Over the past few videos, we have graphed rational functions, radical functions, and polynomial functions. In this video, I will show you how we can apply the same techniques to graphing a trig function with just a couple of tweaks. So the first tweak is going to be that out of the 5 steps that we normally do, we're going to end up skipping step 4. Trig functions, because of their periodic nature, limits at infinity are not going to exist. So step 4 is not going to be useful. But we will still do step 1, where we will find where the function is undefined. That'll be vertical asymptotes. We'll still do step 2, the first derivative test. That's where we will find where the function is increasing and decreasing, and if there are any extrema, like relative max or min. We will still do the second derivative test to find where the function is concave up or concave down, and we will identify any points of inflection, and we will still find the x and y intercepts. First, let's find where the function is undefined. This will be where the denominator is equal to 0, so let's go ahead and set 1 plus sine x equal to 0. Subtracting 1 from both sides, we have sine x is equal to -1. Let's draw a quick unit circle to help us better think about what's happening. Sine is the y value on the unit circle. So where is the y value going to equal -1? We're talking about this position right here on the unit circle. This is where the sine will equal -1. This is where the y value is -1. So we have to be careful about what we call this. If we go this way around the unit circle, we would call this position 3 pi over 2. But what if we went the other way? In this case, this same position would be called negative pi over 2. Remember that the graphs of sine and cosine repeat every time you go a distance of 2 pi. So we are only going to sketch the graph of one period of this function. So we can sketch any interval that has a distance of 2 pi, a length of 2 pi. We've just found a very key position here at negative pi over 2 or 3 pi over 2, depending on how you look at it. This is where the vertical asymptotes will be. So we might as well sketch the graph from vertical asymptote to vertical asymptote. So we might as well pick a period to graph that runs from negative pi over 2 to 3 pi over 2. So this is the interval that we're going to graph. Notice, if I go from negative pi over 2 all the way around to 3 pi over 2, that does take me one full time around the unit circle. So at a glance, you can visually see that this has a length of 2 pi. Anyway, the function will be undefined at negative pi over 2 and 3 pi over 2. So this is where the vertical asymptotes will be. Let's move on to the first derivative test. So this is a quotient, so let's go ahead and do the quotient rule, which says we need to first take the derivative of the numerator. The derivative of cosine is negative sine. That is just something that we have memorized. And then you multiply by the denominator unchanged. So we will multiply by 1 plus sine x. Then the quotient rule says subtract, and we sort of start over. The second time around, we leave the numerator unchanged, and we multiply by the derivative of the denominator. Well, we can ignore the 1 because the derivative of a constant is 0. The derivative of sine is cosine, so this will just be cosine. And then we are supposed to divide by the denominator squared. So we're going to put 1 plus sine x quantity squared in the denominator. This is an expression for the first derivative. Let's see how much we can simplify. Let's do the distributive property. So negative sine times 1 will be negative sine. Negative sine times positive sine will be negative sine squared x. Okay, minus cosine squared x, because cosine times cosine is cosine squared. And in the denominator, we will just leave this 1 plus sine x squared. Now, over in this area, I am seeing something very close to the Pythagorean identity. I would love to get sine squared plus cosine squared happening. And we can do that if we factor out a negative 1. So I'm going to have my negative sine x here, but now I'm going to put in parentheses, and I'm going to factor out this negative 1. I don't really need to write the 1, but I'm factoring out a negative 1, and that's going to leave sine squared x plus cosine squared x. And you can sort of imagine that if I did the distributive property, it would turn it right back into minus sine squared minus cosine squared. So I haven't changed anything. 1 plus sine x squared. Now I can use the Pythagorean identity. We memorized a long time ago that sine squared plus cosine squared is equal to 1. So this will become f prime equals negative sine x minus 1 over 1 plus sine x squared. I'm seeing that I have 1 plus sine x down here, and up here I have sine x minus 1. If I could get sine x plus 1, I could cancel out a factor. So I think I'm going to use that same trick again of factoring out a negative 1 outside of the parentheses. So if I do that, I will have f prime is equal to, I can pull this negative sign out front. I guess I could just put the negative 1. And that's going to leave me with sine x plus 1. Again, you can see that if I did the distributive property, I would get right back to negative sine x minus 1. So I have not changed anything. And then here I have 1 plus sine x quantity squared. Addition is commutative, so it doesn't matter. The sine x plus 1 and the 1 plus sine x, these are still the same factor. I think I'll just go ahead and show the extra step just for my OCD people. Okay, so I can write this as 1 plus sine x, of course. And then in the denominator, I have another 1 plus sine x, but actually I have 2 of them. But because I have that same factor in the numerator and the denominator, I can cancel out one factor from each. So that is just going to leave me with negative 1 over 1 plus sine x. So this is my expression for the first derivative. In order to do the first derivative test, I need to find where the first derivative is equal to 0. I'm finding critical numbers. And I also need to know where the first derivative is undefined. Well, there will be none of these. When we have a fraction and we want to set it equal to 0, normally we set the numerator equal to 0. But there's a constant there. There's no way for negative 1 to equal 0. So we will have no solution from setting the first derivative equal to 0. On the other hand, if I want to know where the function is undefined, I will set the denominator equal to 0. So I will have 1 plus sine x is equal to 0. The only thing is we already did this. Okay, remember at the very beginning, the original function had the same denominator of 1 plus sine x. So we already know that we have vertical asymptotes here and here. So there are really no critical numbers, and we will just use the vertical asymptotes to form the interval. And remember, there's really just one interval. Normally we will do a test value to the left, and one in the middle, and one on the right. But remember, we are only graphing the interval from negative pi over 2 to 3 pi over 2. We're not graphing anything outside of that. So we only need one test value for the first derivative. And you know what? 0 is between negative pi over 2 and 3 pi over 2. So I'm definitely going to use 0 as a test value. So let's evaluate the first derivative and see what happens. So we have negative 1 over 1 plus sine x. So that's going to be negative 1 over 1 plus sine 0. And while I'm at it, I always like to label f prime to show that on this side of the line we are evaluating the first derivative. So this will become negative 1 over 1 plus. So what is sine of 0? Don't forget that sine is the y value on the unit circle. So at 0, the y value is 0. So I'm just going to end up with negative 1 over positive 1, which is definitely a negative value. This tells us that the function will be decreasing throughout this interval. Let's move on to the second derivative test. First, I would like to rewrite the first derivative. There's no need to use the quotient rule when you just have a constant right there. The easiest thing to do is to rewrite this as negative 1 times 1 plus sine x to the negative 1 power, which would be the same thing. So if I want to perform the second derivative, I can just use the chain rule. So negative 1 times negative 1 will be a positive 1. Okay. Now I need to decrease this exponent by 1. So this is going to become negative 2 power. But then I need to multiply by the derivative of the inner function. And the derivative of sine is cosine. So the second derivative will be equal to cosine over 1 plus sine x squared. Next, we find the possible points of inflection by setting the second derivative equal to 0 and by finding where the second derivative is undefined. To set a fraction equal to 0, all you do is set the numerator equal to 0. So we can just set cosine x equal to 0 and solve this. Remember that cosine is the x value on the unit circle. So where is the x value going to equal 0? That's going to happen here and here. So this point at the bottom, depending on which way we go, if we go counterclockwise, this is going to be your 3 pi over 2, which we already know is the asymptote. If we go clockwise, that's negative pi over 2. So these are the two values that we had right from the beginning where the function is undefined. So these are solutions for sure. So x equals negative pi over 2 and x equals 3 pi over 2. But these are not really relevant because we already know these are asymptotes. However, the one at the very top is brand new. X equals pi over 2. This is a possible point of inflection. So let's jump up to the chart, and we're going to do our second derivative test down here, so we'll label it that way. We just found that pi over 2 is a possible point of inflection, so we're going to put that on the number line right here. So we do have two intervals that we will need to test. We might as well use 0 again as a test value, but we're also going to need a value between pi over 2 and 3 pi over 2. Sometimes it's helpful to stare at a circle while you're doing this. So here's pi over 2 and here's 3 pi over 2. What is a nice convenient value between here and here? Hopefully you were just thinking pi. That's a perfect value to use between pi over 2 and 3 pi over 2. So I'm going to use pi as the other test value. So I need to evaluate the second derivative at 0 right now. And remember, here's the second derivative. So I'm doing cosine 0 over 1 plus sine 0 squared. Because of the way the denominator is squared, you know that the denominator is going to be positive no matter what. So we don't have to think about it too hard. The cosine of 0, remember, here's 0. The cosine is the x value. So the cosine of 0 is 1. So that is a positive value. So that tells us that the overall value is positive. And since this is the second derivative, that means that the function will be concave up in this interval. Now let's check, let's evaluate at pi. So we will have cosine pi over 1 plus sine pi squared. Again, the denominator is automatically going to be positive. What about the cosine of pi? So the cosine is the x value, and over here on the left, that's negative 1. So the numerator will be negative, so the overall value will be negative. That means that the function will be concave down in this interval. Notice that we have a possible well, not possible. We have a point of inflection right here at pi over 2 because the function goes from concave up to concave down, and there's no asymptote here, so this will be a point of inflection. And so the point of inflection will be at pi over 2, comma, something. Let's go ahead and find the y value. So we will evaluate the original function at pi over 2. So we're doing f at pi over 2. So that will equal the cosine of pi over 2 over 1 plus sine pi over 2. So the cosine of pi over 2 is going to be 0. Where's my little diagram? Cosine is the x value, so that's going to be 0, which really tells me right now that the value is going to be 0. But the sine of pi over 2 is the y value, and up at the top there, the y value is 1. But this is going to be 0 over 2, which equals 0. So that tells me that the y value is 0. So there is our point of inflection, pi over 2, comma 0. The last information that we need is the x-intercept and the y-intercepts. Remember that we find the x-intercept by setting the function equal to 0. If you want to set a fraction equal to 0, all you do is set the numerator equal to 0. So that would give us cosine x equals 0. But wait a minute. We already solved the equation cosine x equals 0 back when we were working on the second derivative test, and we got these three solutions. So we already know that these two are vertical asymptotes. The pi over 2 turned out to be a point of inflection. So the point of inflection is also the only x-intercept. Let's move on to the y-intercept. We need to evaluate the function at 0. So f at 0 will equal cosine of 0 over 1 plus sine 0. Well, cosine at 0 is 1. Remembering that we're talking about this position on the unit circle, and cosine is the x value, so that's going to be 1. The sine of 0 is 0, since that's the y value right here. So this is just going to give us 1 over 1, which equals 1. So the y-intercept is going to be 0, 1. All right, let's go ahead and get this graph going. So here is our point of inflection at pi over 2, 0. And you see I've drawn the asymptotes in. Let's take a quick look at our chart and see where the function is increasing and decreasing, and where it is concave up versus concave down. So remember that our function should be decreasing the entire time, but it should start off concave up, and then at the point of inflection, it should turn concave down. So here you can see I've drawn the first portion of the graph, concave up, but also decreasing. So now I'm going to draw the rest of the graph concave down while still decreasing. And I threw the old y-intercept in there for good measure. So that's it. This is what the graph should look like. Let's go ahead and compare it to the actual graph off of Desmos and see how we did. As you can see, we nailed it.